Welcome to the BIG I.D.E.A.S Virtual Event, Discover the Value of Design Simulation, provided by Imaginate Technologies. In this presentation, we're going to focus on the Simulate While You Design aspect of simulating workflows inside of Autodesk Inventor Professional. My name's Rusty Belcher, and I'll be giving you the presentation today. In this presentation, we're really going to focus on the workflows available for simulation inside of Autodesk Inventor Professional. We're going to focus on the stress analysis capabilities at the part level. Stress analysis allows us to execute a Von-Mises stress-strain analysis on our design by applying loads and constraints to the part. We can analyze for things like displacement and safety factor and see how our part is going to hold up under the expected load. At the assembly environment, we're going to focus on dynamic simulation, and we can get a lot of information from dynamic simulation. We can actually get the motion and the motion loads of our part as it's working in the different time steps that our mechanism will go through. We can also analyze for things like acceleration, velocity, and position. Our presentation today is going to focus on this little trebuchet. This is a desktop model that you can put on your desktop and throw a rubber ball across the room. Before I start this part of the presentation, though, I really want to give credit to the author of the model and the demo that you're going to see today. This demo and model were created by John Helfin of Autodesk, and I definitely want to make sure to give him the credit for producing the data that we're going to look at and analyze today. So what you're looking at here is a little desktop trebuchet or a catapult. Right now in the Inventor Assembly we're looking at, we've used milled aluminum instead of wood to generate this little desktop model. The overall size is about 7 inches wide by 9 inches tall. Now this is just a regular Inventor assembly. We've used typical Inventor constraints to put it together. And I want to do some analysis on this particular arm to see what the possible loads are and how the stresses will be distributed across the part. Now, there's a couple of different ways we can do FEA simulation inside of Inventor. And the first method I'm going to show you is a typical wild guess. It's quite often necessary to guess what is the maximum load the part will ever encounter during its use. And typically, as designers, we would then bump it up by a factor of 2 or 3, knowing that you would never put that much weight on a particular part. But that's what we want to check for in this particular aspect of the design. So I'm going to right-click on this part, and I'm going to select Open. We're going to open it in its own part window. And our first example of FEA is going to be at the part level with stress analysis. Inventor Professional provides this ability at the part level. Now when we come into the environment, we have a stress analysis ribbon and most everything is grayed out. That's because we have to create a simulation. I'll go ahead and create a simulation. In this example, we have really two options. We can do a single simulation or we can do a parametric simulation. A single simulation allows us to add the loads and constraints to the part and run a simple single simulation. The parametric simulation allows me to define a parameter, like the thickness of this part, and we can define variations for that value and run multiple simulations to determine the most optimal version of the design. Now for this example, I'm just going to run a single simulation. And you can see my browser populate with the necessary nodes for the simulation. You can see material, constraints, loads, contacts, meshes, and results. And if you look at the ribbon, it kind of mirrors this from left to right. We have Create Simulation, Materials, Constraints, Loads, Meshes, and Simulate. And whether you work top to bottom in the browser or left to right across the ribbon, this is the typical workflow of developing an analysis with FEA inside of Inventor Professional. So the first thing I want to do is assign my materials. The materials are automatically brought over from the Inventor Assembly, but we do have the ability to override the materials with any of the material types that you have available inside of Inventor. And it is important to note that you can add any material to the Inventor application. The next thing we want to do is add a fixed constraint at this center hole. You'll notice that as we add the constraint, it actually shows up in our browser. Just like all of the other browser environments that we have inside of Inventor, anything we do in the model will show up in the browser as well. Now I want to add the force on my part. And to add a force, you simply select a face. In this particular case, the direction is automatically applied, but you can come up and select any edge in the file to apply a specific direction. Now this is not the exact direction I want, so I'm going to have to use the Vector Components option. This allows me to define a direction based on my UCS coordinates. And I'm going to put in 150 pounds on the Z-axis, and I'll click Apply. And here you can see the direction is what I want. I'm going to add the same value over here for a total of 300 pounds, which is far more than this part will ever encounter. I'll click OK, and we've got our loads on our file. Now the next thing I want to do is execute the mesh. So I'm going to go ahead and click the mesh view. And if you're new to FEA, if you're wondering how this actually works, let me try to explain it simply. The mesh command actually divides your part up into small little triangular nodules. And the forces that we've applied are mathematically sent from one nodule to another as it crosses your component. So that's quite a bit of math that the computer has to do to give you the final result. Now you might have a particular feature that the mesh is just a little too large. A smaller and tighter mesh is going to give you a more accurate result. So I actually want to refine the mesh in this particular area. To do that, I'm going to use the local mesh control. This allows me to select a face and type in an element size. I have to recalculate my mesh. We'll simply update that. And here you can see we have more triangles in this particular area. Now just a little word of warning, the more triangular nodules you have in your design, the longer the calculation is going to take, but the more accurate your result will be. So now we're ready to execute the simulation. I'll select Simulate and then Run. All the forces will be calculated and we'll get the result of our analysis. Now before you might be shocked at the actual deformation that appears, I do want to make a point that this deformation is adjusted about 10 times from what the actual would be. If I set it to actual, you can see it's just a slight deformation. You can also set it to 5 times normal, which is just ridiculous amount of deformation. I'm going to set it back to actual, and we can zoom in and see how our part how the stresses are being applied to the part with the loads that we've specified. Now you can analyze very quickly for the maximum value. We can come in and see that we have a hole right here, and we've actually got a stress blister here. One of the high spots is at the little hole right there. That's actually a rubber stopper. I can analyze for the minimum value. We can see where that's at, and we can actually select a probe and select any face we want and find out what the value of the stress is at that position. We can also animate our design, so we can actually put it into motion and we can see how the part is going to update as the stress is passed across the faces. Not only do we see the colors change automatically and the motion in the part change, but we also see the values of our probes change. So let's take a look. This is a von Mises stress strain analysis. Let's take a look at our other results. We automatically solve for first principle and third principle stresses. We also solve for displacement, and as you can see, the maximum displacement is down at the right end of our part. We also automatically solve for safety factor, and this is where I want to focus. We actually see here that our minimum safety factor is less than 1. And in typical analysis results, we would regard that as a failure. Anything less than 1 basically is going to mean that our part is going to basically fail, or it won't snap back into its original state. So what can we do to improve our overall design? Well, we have a pocket in the design, and the pocket is basically there just to lighten the material. What I'd like to do is run another simulation and remove that particular pocket. Well, that's very easy to do inside of Inventor. We can simply right-click on the simulation and select Copy Simulation, and this makes a second version of the simulation. Everything's copied over, the loads and the constraints and everything. We also have access to our model features. So I can go right into my model features, find the pocket, and select Exclude from Simulation. That feature is removed along with any child features automatically. And then we can simply run the simulation again. Now in this case, it's going to generate the mesh and the calculation at the same time. We can see the results back in the VOM-EC stress. And I'm very concerned about the safety factor, so we can go right into the safety factor and see that now we are just barely above 1. Now I want to make a point that during this FEA analysis, we have been guessing at what the maximum load would be, and we have been multiplying that far beyond the expected load that this part will ever encounter. There is absolutely no way this part's going to ever catch 300 pounds in its design. So typically I would be concerned with a safety factor of 1. We would want that higher than 1. But for this example, we've actually modified the safety factor just a little bit. So now I want to generate a more accurate FEA analysis of this arm. And to do that, I want to use dynamic simulation. I'm going to finish this analysis, and we're going to close the part. And we're going to go back to the assembly. The dynamic simulation part of Inventor Professional happens at the assembly level. I'm going to go into my environments area, and I'm going to start the dynamic simulation environment. Now, a lot of things happen automatically when you go into dynamic simulation, and I want to cover those as part of this presentation. If you look in the browser, our parts are divided automatically into groups. Any parts that are unconstrained or completely grounded come into the grounded group automatically. Any parts that are free to move or can pivot go into the mobile groups. Also, any constraints that represent typical joints are automatically converted to joints. The simulation environment is concerned with joints, not constraints, and we'll cover the difference of a joint and a constraint a little bit later in this presentation. This example also has force joints automatically built into it, where parts have contact with each other. Now these are added manually, and I will show you how to do that as part of this example. And we also have external loads like gravity to consider. Gravity is extremely important in a catapult design. Now I want to show you how all of this was developed. In order to do that, I'm basically going to erase what I have and start again. So I'm going to go over here to the simulation settings, and I'm going to uncheck to automatically convert the constraints. I'll click OK and put everything back to a basic state. Here you can see that everything now is in the grounded group. There is no mobile group or joints, and we actually have our gravity. And just to make sure, I'm going to suppress gravity. I'm going to turn it off for this example. So this is the beginning. This is typically a base setting for a dynamic simulation. I'm going to go back and turn on this automatically convert. This is a huge time saver. This will automatically convert my constraints into simulation joints, and I definitely want to take advantage of that. And as I said before, the items are automatically split up. Everything that is grounded or completely unconstrained goes into the grounded group. And it's important that you note here the projectile is actually in the grounded group because it doesn't have any constraints. Our mobile groups are created automatically, Anything that has a freedom of motion is automatically placed into the mobile group, and our constraints are automatically calculated into joints. Most of these are just inserts that have become revolution joints. So very good. So just like modeling inside of the typical Inventor Assembly environment, when I add a constraint, I like to spin the assembly around and make sure the constraint's performing as I expect. And we want to do that in the simulation environment as well. So I'm going to go up here to dynamic motion, and this allows me to simply drag parts around and apply forces on them and see how they would behave, and allows me to check the joints and make sure that they are working as expected. And I can see these revolution joints are giving me my typical function in the design. Everything seems to be revolving as desired. Some of the parts are bleeding through each other. We'll fix that in just a minute. But things seem to be working as expected. Now I'm going to click the delete button, and it puts me back into the regular simulation player. Now if I were to run a simulation right now, nothing is going to happen because we haven't defined any forces in this particular design yet. So I'm just going to stop this and back it up and go back over into my construction environment. The construction environment allows the browser and the ribbon to become active. And we want to add our forces into this design. The main force that I'm interested in with a catapult design is gravity. So I'm going to turn my gravity on. We'll basically unsuppress it. And you can define the direction of gravity just like you could define a force direction. I showed you that a little bit earlier. Or you could actually come in and use particular vectors in the assembly. Now I want my force direction to go down, so I'm going to use that corner. But if I wanted to define it based on the z-axis, I could easily do that with the vector components. So now, when I run my simulation, we can actually see that the weight pulls down, pulls the arm up, and that the throwing arm is thrown up in the air and over the top. We still have a problem as the parts pass through each other, but we are going to solve that eventually. So I can stop the player. I can use the slider to slide it at any point or any time step I want. Very, very nice. But I do need to take into account the 3D contacts that are going on in this assembly. So I'm going to go back over into my construction environment, and I'm going to begin the process of generating these 3D contact joints. Now before I do, I actually want to graph my results. That's one of the main benefits of the dynamic simulation environment, is that we can harvest mathematical proof that our design's working the way we'd expect. So I'm going to start my output grapher. This is one of the main tools that we're going to be using in the simulation environment. It allows me to do a number of things very, very nicely. I can analyze, for instance, a particular joint's position, or its velocity, or its acceleration and force. And if you stop for a minute and think, you know, Inventor is a fantastic modeling solution. Great, we can generate any form we want. But what about analyzing for things like acceleration and velocity? How do we do that? Well, in this example, I'm actually going to add a trace to a specific part of my design. I'm going to add a trace point right here at the end of the arm. And I'm interested in displaying it, but I want to track its trajectory, velocity, and acceleration. And again, if I stop and have this discussion with you, how do you model a trajectory with regular Inventor? How do you harvest velocity or acceleration? It's very, very difficult to do with a basic modeling solution. We need a tool like dynamic simulation in order to do that. Now for this example, this trace in our design is going to be pink, and I'll click OK. So if I were to go to my side view and run my simulation at this point, we would actually see the trace of the arm as it goes below the ground plane, comes up and over the top. And if I were to go to my trace environment, I can actually track the position on the z-axis and see that it actually does go below the ground plane as we start. Now I'm going to stop this and go back up to the beginning, and I want to take care of this particular issue. So I'm going to go into the construction environment, and I want to add a contact joint between the arm and the floor. To do that, I'm going to use the insert joint command. Now, joints are different than inventor constraints. A joint takes into account resistance and friction, and a typical inventor constraint does not do that. But we have a number of joints to depict all the mechanical situations that you would encounter in a mechanism. Whether it's a cylinder rolling on a plane, or a cylinder rolling against another cylinder, or even a cylinder inside of another cylinder. There are a number of joints available, and they all depict typical mechanical relationships that you'd see inside of a mechanism. The joint that I want is a 3D contact joint, and this simply means that the faces are going to interact with each other. And for this example, my first face is going to be the face of the floor, and my second one is going to be this face on my arm. I'll click OK, and those two will now contact each other during our analysis. So if I go back over to the output grapher, and I start my simulation, in this case, we'll see that the trace goes right at straight, follows the floor, and then up and over our design as expected. Very good. We can actually see that the arm actually bounces on the bottom of the plate as well. So I'm going to stop this and back it up. And we want to add the rest of our 3D contact joints. Again, to do that, I need to get back into my construction environment. And I'm going to zoom in and take a look at the other joints that need to be in place. Again, these are contact joints. The ball has to roll on the floor. We'll apply that one. The ball also needs to contact that particular face on the arm. We'll apply that. And the arm itself is actually going to work or bounce up against this little rubber stopper. So we'll click OK there. Now before I run my final simulation, I actually want to add another trace. So I'm going to clear out the graph, and I'm going to add another trace for the trajectory of the ball. I'm going to right click and add the trace. We're going to put it at the center of the ball. And again, I want to track its trajectory, velocity, and acceleration. And in this example, that trace is going to be green. Just like before, I want to make sure to go in and define the position of the ball on the z-axis. So let's run our simulation. Now, when we do, we actually see that the arm is actually undulating and the ball's not moving at all. And if I were to zoom in here, you could actually see the arm bouncing up and down on the ball. That's because the ball is still grounded. So we'll stop this and put it back to the beginning and go back out to the construction environment. We need to add one more joint to our design, and that's a spatial joint so that the ball can move freely. A spatial joint is the first joint, and basically, as I said before, it allows the part to move freely with respect to the other parts in the assembly. So we're going to select the ball, and in this example, I'm just going to select this back face here. I'll click OK, and now you can see that particular joint added to our standard joints. So let's grab the output grapher now, and let's go ahead and wipe it, and we will start our design. So here we can see that the arm and the ball are both moving across the floor. The arm actually lifts the ball up. And throws it downrange. And in the output grapher, we can actually track the trajectory of the ball along with the motion of the arm. So very, very good. I'm going to stop it right about 1 second. And I want to focus on some of the information that we've harvested. We have the arm information here and the ball here. And we also have our time steps here. I can right-click on any of these columns and select Search Max. And in this particular case with the ball, the model is put at the actual time step where the ball is at its highest peak in its trajectory. So very nice. We can actually define certain time steps. And what dynamic analysis allows me to do is export these time steps to FEA and run an analysis. Now, that's our next step. I want to export the arm at a particular moment in time. I'm actually interested in this area right here where the ball and the arm diverge. And I can see that it's right a little bit after 0.25 seconds there. So before we export, we have to identify a part for export. And to do that, I have to go back into the construction environment. I'm going to select the Export to FEA command and select my arm. Now, in this example, we are just sending out one particular part, and we need to identify the faces that relate to the other components in our design. There are other joints that affect this particular part, and we need to identify the faces. So for this example, revolution 3 is the face right there. Revolution 4 is this face. Revolution 5 is that face. And the last revolution is actually where the little stopper is anchored to the arm. So once I've identified the faces, then I can run our solution. So I'm going to run the simulation just before. I need to let it run one full time after we export a component. We can go ahead and turn on the output grapher. See how things are working. And in this example, I'm going to go for about a full second, and then I'm going to select Stop. So in our output grapher, we actually can expand it and see our parts to export. And here you can see I have the treb arm marked for export, and I need to identify a time step. Now, as I said before, we could come in and select a particular time step. And this is the value of dynamic simulation. For instance, on the arm, I could go to the arm trace, and I could take a look at, for instance, the maximum point of acceleration. I want to know where is the maximum point of acceleration for the arm. And it seems to be right here when the arm actually impacts the stopper. Now that I know that, I could actually export the arm at that particular instance by selecting the time step here. But that's not what I want to do in this particular example. I'm interested in where the arm and the ball diverge. I want to take a look at that particular instance. And I'm noticing that that's right about 0.3 or a little bit after 0.5 right there. So that's the particular instance I want. And to do that, I'm going to generate a series of time steps. I want 25 time steps in the first second. I'll click OK, and those time steps are automatically added to my design. And I can come down and, for instance, 0.24. I can pause it right here and see that the ball is just leaving the arm. So that's the particular time step that I want to analyze. Actually, maybe 0.27 would be a better one to do for this example. So now that I have everything set up the way I want it, I'm going to back my simulation out, and I'm going to return to the regular Inventor Assembly environment. Now, I want to run another FEA analysis, but this time I'm going to run the FEA analysis at the assembly environment. Just like before, we'll start our simulation. But in this example, I'm going to come down and activate the motion loads for the part. You can see that the trib arm is in place, and I can select the time step that I want to analyze. I'll click OK, and the model is placed at that particular time step. And if we zoom around, you can see that we have a lot more information than we had in our first guess. Remember, our first guess, we had no choice but to add more weight than would ever be encountered by the design. But we had to guess at the forces that were acting on the part. But as I come in here, you're going to see that we have external loads, we have torsion in the design, we have some moments that are happening in the design as well. And you can analyze all of this in the loads category over in the browser. You can see the body loads and the remote forces that are placed on our design. So we have a much more accurate state of our part at this particular instance, our time step in the mechanism's cycle. So all we have to do now is run our simulation. It'll take a couple of extra seconds to run the simulation because we have so many extra loads here, but very quickly we have our results. And please remember, these are exaggerated or adjusted at first. So you can actually see we have some twisting going on in the design, and the stress is building up completely different than we saw in our first analysis. I'm going to change my adjustment back to actual, so we have a more realistic version of our design. But if you can remember how this looked in our first iteration, we see the stress built up in a completely different way as the weight is actually applied to the arm. And just as in our first design, I'm going to jump over to our safety factor. And I'm looking for our minimum safety factor. And here we can see that our minimum safety factor is 15. As I said before, putting 300 pounds on this little aluminum arm is, almost ridiculous. There's no way that part would ever encounter that. But the arm is really just throwing a little rubber ball across your desktop. So we have plenty of safety factor for this particular design. Now, as I finish up my presentation today, I do want to focus on one other functionality that we have in the FEA environment, and that's the ability to write a report. You might have to share your simulation with people outside of your Inventor design community. Maybe you have an engineer that needs to sign off on the design and you need to generate a report of your findings. It's very easy to do within Inventor. I'm going to generate a complete report, and Inventor will automatically cycle through all of the analysis types. And there are many analysis types I didn't get a chance to show you in a presentation today. It'll take screenshots of all of that, and it will put them into an HTML report. This HTML report is easily saved to a Word document so that you can send it outside of your Inventor community. Let's take a look at what's available here. You have the analysis name and who generated it, when they generated it. You have the author's name. You have the project information, the physical properties of the model, and the simulation settings. So we have our simulation settings, our mesh settings, our material settings, and we have the conditions, including gravity. And as I just scroll down, you can actually get an appreciation of how much information you can extract from your design with the FEA and the dynamic simulation environments. I'm going to get down to the main results summary, and here we can see the mathematical analysis of our model for von Mises, first and third principle, displacement and safety, and so on. And if I come down, I'll stop by just looking at my safety factors and again seeing the safety factor of 15. So as I finish up, I think it's important that we finish up with this idea that the dynamic simulation and the FEA environment really work together to generate everything you need to know to evaluate your model in a digital prototyping workflow. Before you ever commit to manufacturing parts or cutting material, you're actually allowed to get mathematical confirmation that your design is going to act accordingly based on the forces and loads that you've applied or that it will encounter as it's moving through your mechanism. So I appreciate the time that you've given me looking at this presentation today. If you have any questions on anything you've seen, please contact your local Imagine It Technologies account representative. Thank you.